Final lab, I looked at Felix Baumgartner's jump with Red Bull from the stratosphere down to Earth. The goal of this jump was to break the speed of sound in freefall. And this simulation was impossibly hard to construct with our knowledge of Python obtained in class. There were just too many factors changing at once, not to mention the auto-scaling feature of Python just wasn't doing the trick. Nonetheless, I'm going to answer 4 questions and show you the first 40 seconds or so of that simulation that are in fact correct. Question 1. How and why did he reach the speed of sound so quickly when terminal velocity would have been slowing him down and not allowing him to reach that velocity? Number 2. What model of air resistance should we use? Number 3. How does air density factor into our resistance calculations? And number 4. How does temperature affect his falling? The data we had to go off were some initial conditions. He jumped from about 39,000 meters, his mass was 117 kilograms. We used Wolfram Alpha to determine some densities of air at various altitudes, and we knew that he deployed his chute after 36,000 meters, about 3,000 meters above the ground. And finally we knew this max speed he obtained on the way down was 372 meters per second, about Mach 1.24, or 1.24 times the speed of sound. For air resistance, we incremented the initial air resistance 0.018 linearly until it reached the final air resistance at 3,000 meters above the ground. So to start, why did he reach the speed of sound so quickly? A few reasons. 1. The speed of sound is not a constant quantity. At lower temperatures and lower densities, sound travels more slowly. In fact, at the density that Felix jumped at, the air was so thin that without the suit, he would have exploded because his blood would have boiled. One quantity that didn't change much was acceleration due to gravity, which, as high as he was, only decreased down to about 9.6 meters per second squared. So we needed to get up to 308 meters per second to break the speed of sound. With air resistance so low that we'll leave it out for the first 30-40 seconds or so, 308 divided by 9.6 equals about 32 seconds to reach the speed of sound. As you'll see, it takes him about 40 seconds in our simulation, and it took him about 40 seconds in reality. Next question, what model of air resistance should we use, and how does air density affect it? This is the hardest part of this lab. Air resistance is a function of air density, which is a function of both altitude and temperature. The viscous air resistance model would work here, but the data just isn't obtainable. Another key point here about friction and terminal velocity. Jumping out at such a high altitude allowed Felix to break the speed of sound and accelerate further past it even. Before the air got thick enough to slow him down and introduce a terminal velocity, he just kept accelerating past the speed of sound. In trying to factor in speed of sound, I looked at a bunch of different formulas, Stokes' law, viscous drag, but these things just couldn't incorporate temperature and the density of the air, and just various constants that I didn't have. Finally, how does temperature affect his falling? Like I already said, temperature affects air density, which is a factor in air resistance. Determining heights for the function, or determining the function for temperature at these heights just couldn't be done in this lab. Temperature doesn't increase or decrease with height. Sure, it gets colder as you go up, but then if you keep going up, which Felix did, you encounter an area in the atmosphere where heat is contained by greenhouse gases and other gases. I'll show you some of the code, but it didn't yield very conclusive results. Felix fell for 260 seconds before deploying his chute, so the while loop runs for 260 seconds. We estimated an average acceleration due to gravity of 9.7 meters per second squared. The code calculates the net force on him and updates his position. The simulation ends when he deploys his chute about 3,000 meters above sea level. When we run it, you see the graph of his position versus time is incorrect. It has him deploying his chute well below sea level. The main reason for this is that he didn't fall at his max speed the entire jump. Once he reached his max speed of about 372 meters per second, he began to fall through thicker air and his speed decreased dramatically. Our simulation doesn't account for this. When we look at the CSV file, however, he reaches the speed of sound after about 43 seconds. Remember, the speed of sound was about 308 meters per second. In reality, this is very close to the actual time it took him, about 40 seconds.